Okay, so I am just going to go through a few things in Chapter 5, Section 1, hoping that it might help you with polynomials. So they give you a basic formula for the polynomial. You've got your lead term here. The largest exponent is called your degree. And then you've got your lead coefficient here. So all of these coefficients have to be real numbers, non-negative. They have to be positive integers. So graphs of polynomials, if you look at the top one, you've got this nice, smooth, continuous curve. But then down here, this is definitely not a polynomial. You've got a corner. This cusp, we've talked about this a little, when you go from concave up to concave up. A gap, which we call a jump, and a hole. If you have any of these things, it is definitely not a polynomial. Okay, so let's start out with a really nice quadratic polynomial, very simple, and they can ask you a whole bunch of different questions. I decided to graph it. You can see down here, I've got a nice little graph, and here's the window that I used. I used a y-min of -60, because I knew the y-intercept would be -56. So how many terms does this polynomial have? Remember, terms are separated by pluses or minuses, and so 1, 2, 3 terms for this polynomial. The degree is the largest exponent that you see, so this is going to be a degree 2. You always want to write your polynomial in descending order of the exponents. That's called standard form. So that's why I have my largest exponent, or my degree, first. Turning points. A turning point is going to be a minimum or a maximum. It's where the curve changes from decreasing to increasing, or from increasing to decreasing. And the number of turning points, if you compare the degree to the number of turning points, the number of turning points is always one less than the degree. They start talking about end behavior, and the notation gets a little tricky. Over here, where you have x arrow infinity, that means the right end behavior. It means as you're looking at the x-axis over towards positive infinity, over in this area, you can see that the function is going up to positive infinity. So as x approaches infinity, f of x approaches infinity. This terminology over here means on the x-axis as you're going towards negative infinity. That means left end behavior. So if you're looking at the graph, the left side of the graph is going up to positive infinity also. And according to the fundamental theorem of algebra and Carl Friedrich Gauss, he said if you look at the degree, then that polynomial could possibly have 2 solutions. Subtract 2 from that, and it might not have any real solutions. That graph might be totally above the x-axis. I went ahead and found the x-intercepts, which are -7 and 8. And if -7 and +8 are real solutions, then I know x plus 7 and x minus 8 are my binomial factors on this. So let's look at even degree polynomials. This is a quadratic, degree 2, and a positive lead coefficient means concave up like a cup. Over here, a negative leading coefficient, concave down like a frown. This has a degree of 4. This is a degree 4 polynomial. And some students just kind of like to trace the polynomial, and you can see one path is decreasing, and then the second path is increasing, the third path, and the fourth path. So there are kind of 4 what we call paths, and then on a degree 4. And you could also look at 3 turning points, also indicates this is a degree 4 polynomial. The end behavior is going up. That means you have a positive lead coefficient. When the end behavior goes down to negative infinity, you have a negative lead coefficient. Now this is totally different with odd polynomial degrees. So over here, you can see that one end goes up and the other end goes down. So when you have a positive leading coefficient, the graph starts off in an increasing fashion, okay? Starts off increasing and goes up to infinity. Over here, an odd goes up, down, up. It's starting off increasing. With a negative lead coefficient, it starts out decreasing. You can see here, decreasing. So let's take a look at an example. Which of the following could be the graph of a polynomial? The lead term is -3 and the degree is 4. So a degree 4, look at this one. 1, 2, 3. No, that doesn't have 4 paths. How about here? 1, 2, 3. No, I'm going to eliminate A and B because the degree 4 indicates there needs to be 4 paths or 3 turning points. But now I'm with B and D. I'm going to look at my leading coefficient, -3. So right here, I can see my end behavior is going down, so B is going to be my answer. If my leading coefficient had been positive, I would have chosen D. So let's discuss multiplicity for just a minute. On this polynomial, I've got x plus 6 and x minus 7. And if you'll notice, the exponent by each of the binomials, in this case, is a 1. Okay, that's an odd multiplicity. That means the graph is going to cross the x-axis at -6 and +7. It touches the x-axis only once. It crosses it. And I think MyLabs Plus uses the word crosses. On this example, the multiplicity is odd, 1. So at -6, I'm going to cross. But look at the degree here, the exponent, or as we call multiplicity, not degree, sorry, multiplicity is even. That means the curve is going to touch the x-axis at +7. It kind of bounces off. It's going to hit 7 twice, and MyLabs Plus says it's going to touch. So cross and touch. Notice again, multiplicity 2, at -6, it's going to touch. At +7, it's going to cross. On this example, even multiplicity, the graph is going to touch at -6 and touch at +7. And you'll notice that over here, -6 is counted twice and +7 is also counted twice. And Gauss says that a degree 4 polynomial should have 4, 2, or 0. And in this case, it actually has 4. -6, -6, +7, and +7. Okay, an example. The following shows a graph of a degree 8 polynomial. List the zeros and their multiplicities. So the first 0 is -15, right here. And the multiplicity is odd. It's probably a 1 multiplicity. The root shows up once. -10, see how it touches? That's going to be a multiplicity 2. -5, that crosses, so it's a multiplicity of 1. And you can see -15, -10 occurs twice, -5 occurs once, 0 is crossing, so that's going to occur once. Look over here at 10. See how it's going to just touch? I'm going to count 10, multiplicity 2, and then 15. So 1, 2, 3, 4, 5, 6, 7, 8 real solutions for a degree 8 polynomial. So let's look at this wicked little polynomial. How many terms does it have? terms are separated by plus or minus. 1, 2, 3, 4, 5 terms. The degree is the highest exponent, and I have those exponent in decreasing order, so this is a degree 4. The number of turning points is always 1 less than the degree, 3 turning points. And I went ahead and graphed this polynomial just because I wanted to see what it looked like. And there was the window that I used. I kind of made my y-min and y-max pretty big. End behavior, the right end behavior. Remember, this is math for right end behavior. The right side is going down to negative infinity. Whoop, sorry. And over here, this means the left side. So the left side is also going down to negative infinity. According to the fundamental theorem of algebra, Gauss says the degree is 4. Look for 4 solutions. You might have 4, 2, or 0. In this example, I have 4. So the negative 2 has a multiplicity of 2. I count it twice. Positive 2, the graph crosses, and at 5, the graph crosses. They have a multiplicity of 1. Last example, this is an x cubed. How many terms? 1, 2, 3, 4 terms. The degree is 3, and this will have 2 turning points. The end behavior, the right end behavior goes up to infinity. The left end behavior goes down to negative infinity. According to the fundamental theorem of algebra and Carl Friedrich Gauss, we need 3 real solutions, or maybe just 1, but we do have 3 real solutions. 1, 2, 3, -9, -2, and 4. And I did second calc 5 intersect on that. And if I have -9, remember my binomial factor is positive x plus 9, x plus 2, and x minus 4. Okay, and that is it. So we will go ahead and stop right here. And that's about it. I hope this helped, and y'all have a really good night.